Most programmers spend their careers building applications, but rarely visualize what their data actually looks like when it hits raw hardware memory blocks. This diagram shows a raw memory block. Hidden inside this dark-themed terminal grid is our initial payload. We will trace its algorithmic lifecycle from inception to execution. To understand automated software, we look at execution strictly as sequential pointer mutations across these physical memory states. We will map this concept using a multi-platform autonomous social media engine as our structural case study. This entire high-level pipeline operates strictly as an asynchronous distributed execution graph. The payload will traverse 3 primary logic gates: a database trigger, a large language model optimizer, and an API router. The payload must maintain its structural integrity as it is transmitted across disparate memory environments. The entire sequence must execute with absolutely zero manual input. The data payload must organically mutate its structure to meet the rigid parameters of multiple target platforms. Finally, the system must autonomously verify and log the final state transition back at its origin point. This diagram shows our algorithmic state tracker. We will monitor the payload's memory size and pointer location as it moves. High-level software integrations are the automated management of distributed memory allocation across external servers. The initial state change happens inside the origin database, where a Boolean flag physically flips from a pending status to approved. This visual tracks the exact moment that Boolean flip instantiates an outgoing webhook. The hardware immediately allocates a contiguous memory block for the HTTP request payload. Inside this raw string sits the unoptimized social media topic, securely nested alongside its structural metadata keys. Capturing this payload requires the receiving server to maintain continuous, event-driven, asynchronous listening. This initial database trigger functions as the physical birth of a structured data object inside execution memory. The payload arrives and ingests into the primary execution graph via N8N. It hits a logic gate governing a central AI agent node, forcing new internal processing constraints. The system executes a physical handoff of the single-string payload to an external logic gate, initiating the core transformation sequence. Here, the Claude 3.5 API forces a bifurcation of the payload. This diagram shows the pointer mutations as the origin data struct divides into 2 distinct memory allocations. Path A's memory allocation is optimized specifically for the X platform. It carries a strict 280-character array constraint. This minimal payload size ensures Path A is prepared for immediate, low-latency execution. Conversely, Path B targets the LinkedIn platform. It requires a dynamically sized array to accommodate professional, long-form content. The processor injects specific structural metadata into Path B, defining strategic line breaks for readability. It also appends algorithmic hashtag arrays to satisfy Path B's optimization constraints. The central orchestration node manages both of these concurrent execution threads without causing a memory leak. It then reassembles both distinct branches into a singular, complex HTTP post request. The singular origin application state has successfully forked into 2 divergent, optimized runtime arrays. The newly mutated nested payload pushes to the secondary multi-channel distribution router via make.com. Path A executes a direct memory dump straight to the X API. Path B requires a temporal buffer, suspending the payload for scheduling constraints. Stateless routers handle time as physical storage, holding memory allocations in suspension until constraint parameters are met. The execution loop remains incomplete until the temporal buffer's empty and both platforms publish their payloads. The router receives HTTP 200 execution responses from both endpoints, initiating the final confirmation loop. This tracker captures the return pointers carrying the live URLs backward through the orchestration network to the origin database. This requires a final state mutation, rewriting the initial structural state in the origin database from approved to published. The live execution URLs physically append to the origin record, logging a clear validation track. The system then clears and dumps the temporary memory allocated throughout the graph during runtime. The initial hardware memory block we tracked hits its final resolution and deallocates. A complete zero-touch automation loop is a precise circular journey of physical memory allocation, mutation, and eventual state resolution. This diagram contrasts the ephemeral routing pipeline mapped with an alternative architecture, a persistent memory AI assistant. The pipeline traced dumps memory upon completion to preserve server efficiency. A 2-hour AI assistant build requires maintaining continuous persistent chat context across independent API calls. Context persistence operates as a hardware problem of continuous memory alignment and sequential block retrieval. Optimization parameters change when a memory allocation must grow dynamically with every single user interaction. The core architectural difference between stateless routers and intelligent assistants is dictated by how data serialization and memory alignment are managed over time. The orchestration we have tracked shows how these high-level abstractions operate as a series of data layouts and pointer mutations. Inefficient asynchronous logic graphs generate hidden memory footprints that impact execution time. Direct, authoritative tone. Examine your own orchestration graphs and refactor your logic trees to minimize runtime and memory footprints. Visualizing these physical hardware constraints makes the internal logic of complex software visible and manageable.